So the final periodic property in periodic trend that the IB could ask you about is called electron affinity. Now, it's definitely one that you need to know by definition and be able to represent in a chemical equation. It's not one that I've normally seen asked about, or certainly it's not very common for them to ask you to explain the trend, because the trend has a lot of discontinuities, a lot of sort of anomalies to it, similar to first ionization energy, but actually even more complicated just because of the nature of electron affinity. So what is electron affinity? Well, it's basically the opposite of ionization energy. When we had ionization energy, it was the energy to remove a mole of electrons from a mole of gaseous atoms, and it was the energy change associated with that. So we say the delta H. This represents a term called the change in enthalpy, which for now we can just treat like the change in energy. The electron affinity is the energy change when a mole of gaseous atoms gain a mole of electrons and form negative ions. So instead of, this is about electron loss, and this one is about electron gain. But otherwise, the definitions are essentially the same. It's a little bit like electronegativity, but electronegativity is not an energy amount. Electronegativity is looking at these two atoms are bonding, where are the electron pairs pulled, which atom are they more attracted to. That's on a 0 to 4 scale, that's a relative scale, whereas these ones are actually energy amounts. So both of these are energy. Now, a key rule about energy that's going to hold true throughout the course is that anytime we are separating particles that are attracted to each other, anytime we are breaking bonds or removing things from one another, separating them, that's going to require an energy input. So the ionization energy and electron loss, where you're pulling an electron off of an atom, these values are always positive. So these are known as endothermic values, that energy has to be put in to break this bond, to break the attraction between the electron and the atom. So energy must be put in. Whereas the opposite is generally true for the electron affinity values that are listed in the data booklet. When an attraction is formed between two particles, that is pretty much always going to release energy, usually in the form of heat, and so we call those changes exothermic. So endothermic is breaking apart or separating, and exothermic is bringing together. It's a pretty good rule of thumb to hold true for the entire course. Okay, so I've written the chemical equation representation for hydrogen, and then the chemical representation for the ionization energy on the right-hand side. Now, generally, these two properties will follow the rules of effective nuclear attraction. So that means when will we see the effective nuclear attraction increasing? We're going to see that as we have less energy levels, right, which is also equivalent to having smaller radii. So when particles are smaller, we expect their nuclei to attract electrons more. We also know that if we increase the number of protons, assuming the energy levels are the same, if we increase the number of protons, then we know that the positive charge of the nucleus is going up, and therefore we expect the effective nuclear charge to go up as well. So these two rules about effective nuclear charge that hold true for radii and electronegativity, they generally hold true for these two properties as well. When we have smaller atoms with less energy levels, and therefore less shielding effect also, we expect the attraction between the electrons and the nucleus to be greater, and therefore we would expect ionization energy to be higher, and also electron affinity values to be greater. Now, they are going to be negative because they're these exothermic values, and so when energy is released from a system, we say that the energy change is negative because they are releasing and losing this energy to their surroundings. So in terms of the magnitude, both of these things are going to be bigger. So we'd say we're going to increase the electron affinity. But when I say that, I mean it's going to get more negative. More energy is being released. So it gets kind of tricky when we talk about negative values. But both of these values increase as the effective nuclear charge goes up. And so we should see that towards the top of the table, and then towards the right-hand side of the table, where we increase protons, we should see the highest electron affinity and the highest ionization energy values. If we look in the data booklet, that's more or less what we see. So the first ionization energy values are listed at the top left corner. And as you go from hydrogen to helium, you see that increase because of the increase in the number of protons. You see that general trend as you go across any of the periods. As we increase the number of protons, we see that we're increasing the attraction, and so we increase the ionization energy of the elements in general. We also see that the electron affinity values are more or less doing the same thing. I've got a minus 60 here. Notably, there is no value for beryllium. We'll come back to that. It goes down a bit for boron, which is a bit funny, but then it goes up for carbon. There's no value for nitrogen. It goes up for oxygen, and then it really goes up for fluorine. So again, with this new property of electron affinity, we're seeing that it sort of follows the rule in general of effective nuclear attraction. And then we also see going down the table as we increase our energy levels / shielding effect / radii is increasing. All of those things are lowering the effective nuclear charge. And as we do that, we see that ionization energies drop. And we also see that, maybe not as extreme, but in general, these electron affinities are also dropping. So electron affinity is kind of, similar to explain to ionization energy or any of these other periodic properties. It's based on the concepts of effective nuclear attraction. But it is a weirder property because it has more of these anomalies. So I kind of mentioned, and again, I don't think they have you explain these anomalies generally. I've almost never seen a question on this on the IB exam. So maybe the first thing that we would notice is that the noble gases, none of them have electron affinity values listed. But weirder still, we see that nitrogen doesn't have one listed, and then we see that beryllium and magnesium don't have values listed. So why wouldn't these elements have electron affinity values? Why don't they have an affinity for electrons? Well, like first ionization energy, this comes down to looking more closely at electron configurations, including thinking about their s and p orbitals. You can see actually it happens again here with these elements as well. So different elements throughout the table are not listed with electron affinity values. That means they don't really have an affinity for more electrons. Let's see if we can explain why. They actually do have electron affinity values, but their electron affinity values are positive, which means you have to put in energy to make them gain electrons. And I think the IB has chosen to just leave those values off the table because that gets a little bit confusing. So we don't even really have to worry about the fact that they're positive. They do not have EA values. So in other words, they don't have affinity for electrons. So why wouldn't these elements gain electrons, or why, when they do gain electrons, why don't they release energy like the other elements? Well, the reason is their configurations. So if we think about beryllium and magnesium, we know we're dealing with S2 elements. So when an element has an S2 configuration, it has very little attraction for the next electron, because the next electron has to go to the P sublevel. And so the next electron would have to be a P1 electron. And the atoms don't really have enough protons to attract that next electron because it's going to a new sublevel. That new sublevel is farther away. That new sublevel is a little bit more shielded. So that new sublevel doesn't feel the same attraction to the nucleus. So that is a similar thing that we saw with the first ionization energy. When we had that P1 electron in boron, it made it easier to remove an electron from boron than we otherwise would have expected. It was actually less energy than with beryllium. And now we're seeing a similar kind of thing come up in the electron affinity trend because of that P1 difference. Then if we go to nitrogen, why doesn't nitrogen have an electron affinity? Well, nitrogen has that P3 configuration. So it's got the 3 boxes, it's got 1 electron in each, and if nitrogen is going to gain another electron, it's going to create this extra repulsion. So there's this electron-electron repulsion that happens with pairing. And so it's very unlikely that nitrogen would become P4. That 4th electron is not really attracted to nitrogen. There's not an attraction there for it to gain an electron. And so we say that nitrogen doesn't really have an affinity for any more electrons. And if you make it gain that extra electron, it won't actually release energy because it's not a net stabilizing change for nitrogen. And the last ones are the noble gases. Why wouldn't the noble gases gain any electrons? Well, they already have full valence shells. So where would the next electron go? Well, for neon, which is 2s2 and 2p6, its next electron would have to go to a whole new energy level. It would have to go to the 3s1. And there's very little attraction, or there's no stabilizing effect of gaining that extra electron. So neon has no attraction for gaining that new electron, and so there's no affinity for gaining a new electron. So the weird things, the weird discontinuities that we see in the electron affinity trend, which again, I don't really think that they would generally ask about this. It would be sort of an extreme curveball type of question, but push comes to shove, if they did, you could look at the electron configuration details and try to justify why those particular elements, because of their configurations, how they already have a complete S2, or they have a half full P3, or they have a full energy level of electrons, the next electron would need to go to a new sublevel, so it would be less attracted. The next electron would create this repulsion in the pairing, so it doesn't experience really an attraction. Or with the noble gases, the next electron would need to go to a whole new energy level, so it doesn't experience an attraction. Even here, what's going on here? These elements are all D10. They have a full D level. And so the next electrons need to go to the higher up P level. So again, we're starting a new sublevel. So gaining electrons, that new electron would be required to go to a new sublevel, which is not, that electron will not be attracted. So atoms, once they have full sublevels or full energy levels, they have very little attraction for the next electron. And that's why we don't see electron affinity values for those types of elements. There are a few other weird things going on with the electron affinity trend. I don't think they're going to push you on the details. But one last thing while I'm here that I'll point out. A couple of elements, this will come back for HL at some point, they have a first value listed. That's the first electron affinity. But as we know, oxygen tends to form a 2- ion, so it can gain more than one electron. The second value that's listed here is the second electron affinity. You can see that's really only listed for oxygen and sulfur, which tend to form 2- ions. You can also notice that the second electron affinity, when you gain a second electron, this value is now positive, which means you have to put in energy to make this happen. It doesn't happen naturally on its own. Now, why would that be? Well, that's because these particles that are gaining their second electron are already negatively charged. And so if you're trying to force something negative onto something that's already negative, that's going to require energy because naturally these two particles are going to repel each other. And so this would be an equation for a second electron affinity. And because there's repulsion, between negative charges, second electron affinity values are always positive. They always require energy because it's not about positive and negative coming together, which should happen naturally and release energy. Negative and negative won't come together unless you put in energy and make it happen. So that's what the electron affinity trend looks like. It's flipped here to show the more negative values being higher up. You can see it's very strange. It has a lot of up and downs. This is not a trend that they typically ask about, but if they did, we could, for the general trends, go back to our normal rules of effective nuclear attraction, energy levels, shielding, radii, and protons to help justify why the value would increase in magnitude. We should be able to write a chemical equation or define it. And this is an energy release, which is listed as a negative energy value in the data booklet. And then the strange anomalies, we could point to similar arguments that we used for the first ionization energy, which is when electrons have to occupy new sublevels or when electrons have to pair up in an orbital, they experience less attraction, and that's why those elements don't have electron affinity values. A confusing trend, probably the least important trend, but hopefully that helps clarify a bit.